Hi, everyone. I'm going to take a little bit of time to give you the background lecture for Activity 4A for AHL topic, looking at two-slit interference. We'll get you started on your activity here. So you can find a full copy of these notes of this document in PDF form online as well, so in Canvas. So we have Young's double slit experiment. This is a really important experiment to be familiar with. It shows up on the IB exam, sometimes as a conceptual question or a multiple choice or a free response. Young's double slit experiment was an experiment in which Young used light and shown it through two slits. And really the big idea behind what he saw was this proof that light has a wave-like behavior. And later on, we'll see that this is also true for particles. So if you do this for a stream of electrons shining through two slits or going through two slits produce the same kind of a pattern, also implying that electrons have a wave-like behavior as well. So if we take a look at this diagram, let's walk through this here. We got some source of waves. So in our case, we can think about this as light. Could be a laser, could be a light bulb, could be the sun, LED, or a source of electrons, particles. And this is important as well, notice that this arrangement has a single slit first that the light can shine through with a very narrow opening. And what this does is this creates a point source of the waves that are passing through. This is not necessary if you have a laser. And the important word to be familiar with is the word coherent. If waves are coherent, then that means that they have the same frequency, that they're in phase with each other. So all the crests line up with crests and the troughs line up with troughs. The waves, well, that's constructive interference. The waves, you look at oscillations that are in coherent with each other. So like if the sources of the waves are both doing this, if they're out of phase with each other doing something like this, we do not have a coherent source. Okay? Or one of them is going faster than the other, we don't have a coherent source. So a laser is naturally coherent, but any waves going through a small opening, we just have a point source of waves, then they'll just be the same waves passing through. We'll have a coherent source. Then we have our double slit, which is what makes it the double slit experiment. And so we have light or waves going through one slit and going through another. And notice that I have three important dimensions here. I've got little d, which is the distance, the spacing between the slits themselves. And then I have the variable little b. We saw this already with single slit diffraction. That's the width of each individual slit. Then I've got big D, which is my distance to the screen, where my interference pattern is going to show up. So we know already, even if the light just came through a single slit, that we're going to end up with diffraction. Light's with some spreading out that's going to happen. We'll end up with a pattern with a central maxima and some additional maxima and then on either side. And this slit's also going to cause a pattern here as well with a central maximum. And when I create these two patterns, these patterns are going to interfere with each other. We'll end up with an overall interference pattern. So let's take a look at what that will look like. And I'll show you here. So here we have, and we've seen this graphic before, we have this idea that if we have two sources, you can think about this as the light coming through either of the two slits, and we find some spot on a screen that is a different distance from each of the sources. If it adds up so that the waves are in phase with each other, or we have whole numbers of wavelengths and difference in length, we end up with a place of constructive interference, which of course would correspond to some kind of a bright spot as the light were to shine through there. Or if we go to another location where one wave has brought a crest where the other has brought a trough, they're out of phase with each other because the difference in distance is a half a wavelength apart, we'll get destructive or a canceling effect that occurs. So this last graphic might be a little more helpful. Here's the overall effect. So we got our source of light going through the single slit to just make it a single point source of coherent light. Then that light travels, we can see that causes some diffraction. It doesn't just make a one line, right? It spreads out because of diffraction through the single slit. And then that coherent light is going to hit these two slits here, and each one is going to act as a source. And so we have our screen over here, we have some different distances, and any place where they both travel the same distance, like the middle here, we'll get a bright spot where they add constructively, or the wave has a little farther to travel from slit 1 and a little less far from slit 2, but if that difference is an entire wavelength, we'll end up with another bright fringe. So we get a series of bright fringes, and we get a place, dark fringes in between of destructive interference. Okay. So what does this look like in real life? We'd have something like this. Here we recognize the single slit pattern, which we looked at in a previous activity. Light coming through a single slit has that central maximum. Then we get the first minima on either side, and you can see, we can at least see another maximum on either side of that. But there are a number of these, they just get dimmer and dimmer. Now, when we shine the light through a double slit, notice it does look very similar between the two patterns. I still see like a big maximum here, and I can see another maximum on either side with a min in between. In fact, the same place we'd see here. But the double slit pattern, the fringes, the light and dark fringes from the two slits are actually these little fine lines in between. Okay, so we have a double slit pattern of fine lines, and then over top of that, we have superimposed a single slit pattern. And it's really impossible to avoid this because each of your double slits also has its own slit width and is causing this single slit pattern to exist simultaneously. So I'm going to jump back to the notes here and see how this plays out. We represent this in our notes. Saw what the pattern looked like here. We see two things with a double slit pattern. We see the tiny bright fringes coming from the two sources, constructive interference from the two sources. These are called fringes. But then these are modulated or bounded by the single slit pattern, which is the width of each fringe, and the diffraction pattern from single slit diffraction. So I have it basically color-coded down here. We can see what's kind of in pink or magenta. We can see the single slit pattern, which is from an individual slit. We see this relationship right here, the angular distance between the center and then the location of the first minimum. This was given on the IB data sheet as lambda over b. This is telling me what that bound is going to be. And then we have in blue right here in the background, the double slit pattern of the fringes created from the different distances from each of the slits. And you can see how the double slit pattern with its slits is being bounded by the single slit with each individual slit. And one of the things we had talked about before, a little bit earlier, was this spacing between bright fringes. S equals big D lambda over little d. Remember, big D is how far the screen is away from my double slit arrangement, lambda the wavelength of light, and little d is the spacing, the gap between the two slits themselves. Okay, so we got these bright fringes and then dark fringes in between. Notice that the central bright fringe matches up with the center of the single slit pattern as well. So this is the kind of thing we'd see with a double slit arrangement. Now, we could do some problem solving with this, or there may be some just general conceptual questions you might see on an IB exam or in our activity. So two common scenarios you should be familiar with is an arrangement where you would vary or change either little d or little b and observe, keep one the same and change the other. So little d, remember, that's the spacing between the two slits themselves. So what if we kept the spacing between the slits the same, but we just made the slits wider or narrower, really like razor blade slits versus slits that are wider? And we see that if we have like very narrow slits, we get a lot of bending or a lot of diffraction, a big diffraction angle. So what it does is it makes our single slit diffraction really wide. And if we take our value of b, the width of each individual slit, and you make it large, then it really narrows down that single slit pattern. But because we haven't changed the spacing between the slits themselves, the blue background pattern from my double slit arrangement, it's staying constant. S being the distance between each of these successive bright fringes. They're all evenly spaced, and it's the same exact spacing in these two graphics. We've just changed that bounding single slit pattern that's limiting it over top. And then conversely, we could keep the width of the slits themselves the same, but just change the spacing between the two slits. And if we do that, that will change the spacing of our fringes, the bright fringes, which are drawn in blue here. So we see the same magenta background curve from the width of the slits, which is B. And then the spacing between them, little d, is changing. So if we make little d really small, then it makes the spacing really far apart. And if we have little d really large, if we have our slits really far apart from each other, then we end up with our fringes very close together. So you'll get a chance to explore this more in the activity. And good luck. I'll be here if you have questions.